Hi fellas, welcome back to the channel. In today's video, we are implementing UART serial communication on the AVR ATmega 2560 microcontroller, the chip behind the Arduino Mega. We will be covering two complete tasks. In task 1, Arduino Mega transmit a number over UART and second Arduino receive it and display it on 16 Express LCD. In the task 2, a button is pressed on the first Arduino Mega, send a characteristic over a UART, and the second Arduino Mega uses the character to control an LED, turning it on or off. Everything is simulated inside Proteus 8, and no physical hardware for the task number 1, but I have done the hardware for the task number 2. So let's get started. So before we look at the code, let's understand UART on the ATmega 2560. Unlike the ATmega 328, which has only one UART port, ATmega 2560 has four independent UART ports: UART 0, UART 1, UART 2, and a UART 3. In our code, we are using UART0, which maps to TX0 pin PE1 for transmitting, RX0 pin PE0 for receiving. They are the same pins used by the Arduino Mega USB to serial chip, which is also why they are the default choice. The registers we will be working with are UBRR0, set the bound rate, UCSRO0B, enable transmitter and or receiver, UCSROC, sets the data frame format, UCSROA, status flag, UDR0, the data register for sending and receiving. We are running at 9600 bound with a 16 MHz clock. Same formula at Atmega 328 because both run at 16 MHz and use the same UART peripheral architecture. And so let's start with the task number 2, the transmitter side. Uh, First of all, we have written the libraries. Standard startup FCPU is defined as 16 MHz, so the delay library works correctly. Now we have initialized the UART ports. So inside the UART initial, UBRR0 is equal to 103. So that means that we have set the bound rate to 9600. TXENO enables the UART0 transmitter, UCSZ01 and UCSZ00 configure 8-bit data frames. Now we can see a void UART send. This means that we wait until UDER0 is set, meaning the transmit buffer is empty and ready for the new data. Then write the characters in UDR0. The UART hardware takes care of the rest. On the Atmega 250, port B, pin 0 is configured as input with the internal pull-up resistor. Enable this mean the pin read high by default. Pressing the button pulls it low. On the Arduino Mega, PB0 correspond to digital pin 53. Now you can see a loop of pin B and UART and H. So in this loop, when the button pressed, PB0 low, send H. When the button is released, PB0 high, send L. 50 millisecond delay prevent false trigger from the button bounce. So now we will going to see the receiver code of our task 2, because I am first doing the task number 2 and then I will shift towards the task number 1. So now we write the receiver code. On the receiver code, only RxEMO is enabled. We only need to receive, not transmit. RxEO flag gets set when a new data arrives in the receive buffer. We wait for it, then read and return the data from UDR0. PB0 is now an output. That is where the LED is connected on Arduino Mega. This is a digital pin 53. Now, when the it receives H, the LED turns on, and when it receives L, the LED is off. Simple and effective. Now, the section 4, we are going to see the Proteus setup of this code. So you can see the task number 2 Proteus. Task number 2 Proteus. So the components are two Arduinos Mega, one push button, one LED. Connection is that the Arduino Mega 1TX0 is connected to the second Arduino Mega 2 RX0 PE0. So the PE1 pin of the first Arduino is connected to the second Arduino PE0. Arduino Mega 1 PV0 pin 53 push button, and then to ground Arduino Mega 2 PV0 pin 53 LED, and then ground. Loading hex file. Double clicking Arduino Mega 1, load transmitted hex file. Double click Arduino 2 and load the hex file. Simulate simulate Now we simulate it. So you can see when we are pushing the button, the LED turns on, and when we don't push the button, the LED turns off. So this is the simple. Now you can also see the hardware picture of this code, that I have also implemented this code in the hardware. So as you can see, when the button is pressed, the LED is on, and as soon as I remove my finger from the button, the LEDs stop glowing. Now we are moving toward the task number 1. So in this we will study a UART with LCD display. So on the first, you can see different libraries that I have defined. So this define maps the LCD data and control pin of the ATmega2560 ports using the custom LCD library format. Data line D0, D3 are on port D, data line D4, D7, RS, and EN are on port C. DDRD is equal to 0xFF and DDRC 0xFF. This means the port D and port C are set as output required for driving the LCD. Initialize the LCD in 8-bit mode using the library LCD8 int on brackets. That means that we have initialized LCD in 8-bit mode, and then you can see a UBRR0103. That means UART0 receive a configuration of 9600 bound. Receiver enable 8-bit data frame, exact same setup for the task 2 receiver. Now unset character C portion, we can see C hold the received byte count is the string buffer used for the LCD display. Wait for the data to arrive, then read it in the while loop. And then in the other line, this is the key step. The LCD can only display string, not raw integers. ITO0 a bracket from the stdlib.h library convert the integer in C into a decimal string stored in counter. For example, if C is equal to 65, count become the string 65. Now in the part, we have writing the cursor and receiver. In the row 1, display the label receiver. Row 2 displays a received number as a string, and 500 millisecond delay keep the display readable. So now we are going to discuss the transmitter code for the task 1, because I have to explain the transmitter code first, but I accidentally explain the receiver code first, so don't worry. And so now let's move on the task one transmitter. This Arduino Mega has an LCD connected to it, and it sends an incrementing counter value over UART via every 500 millisecond. We have defined the memory same LCD ping mapping as the receiver D0, D3 on port D, D4, D7, RS, and EN on port C. The transmitter also has its own LCD, so we can see that value it is currently sending. From DDR-D and DDR-C is equal to 0xFF, we can see that both are set as a output and the LCD is initialized in 8-bit mode. UART 0 transmission configure UBRR0 is equal to 103, that means 9600 watt rate. TXEN 0 enables the transmitter only, no receiver on it. There UCSZ01, UCSZ008 8-bit data frame. Count in an unsigned character and hold the value we transmitted starting from 0. Temp is a character array used to convert the number to a string for LCD display. Before sending anything, the transmitter display the current value on its own LCD. Line 1 show the label transmitter. Line 2 show the current value of a count as a string, saving IT0A. This way you can visually confirm on the transmitter side which value is being sent. Now the actual UART transmission, wait until UDR is 0 is set, transmit buffer is empty. Write count directly into UDR0, the raw byte value is sent over UART. Notice here we are sending the raw byte value, not the string. For example, when count is equal to 5, the byte value 5 is transmitted. The receiver gets the byte, convert it to a string using IT0A. The display is. After sending, count is incremented by 1. The 500 millisecond delay control how fast the counter increment and transmit. So the sequence every 500 millisecond is display current count on the transmitted LCD, transmit the byte over UART, increment count, and then repeat. Since count is an unsigned character, it goes from 0 to 255 and then wraps back to 0 automatically. So now we are going to see the Proteus setup for this task. We can see we have two Arduinos, two LEDs as and a potentiometer. The LCD connection or receiver Arduino or LCD D0 D3 is from PD0 to PD3 and LCD pin PD4 to LCD pins D4 to D7 is connected to PC0 to PC3. LCD RS is connected to PC6 and LCD enable is connected to PC7. The UART connection transmit Arduino Mega TX0 to our receiver Arduino Mega RX0. We load the hex file and then simulate. We can see that the first that thing appear on the transmitter after a few seconds of delay. It appears on the receiver ends. So that's the wrap up of today's video. We successfully implemented UART serial communication on the Atmega 2560, the chip inside the Arduino Mega. In the task 1, we receive number via UART and display it on the LCD using IT0A. Button pressed when H or L over UART to control the LCD on the receiver. Key register that we have used in this video was UVRR0 baud rate register, UCSR0B enable TX or RX, UCSR0C data frames configure, UCSR0A UDRE0 and RXC0 are status flags, and UDR0 data transmit the received data. One important thing to remember that Atmega 2560 has 4 UART. In this lab, we use only UART0, but the same logic applies to all 4. So just swap the register number. If the video helped you, please like, subscribe, and leave any question in the comment. See you next time. Goodbye.